All right, so we're starting. Let me see where we need to be. All right, so system not great. Okay, so welcome to the fourth lecture for deep learning course. So actually, we're going to start with deep learning this week. So the first three lectures were a little bit of preparation to talk a bit about kind of learning theory and some general background about artificial intelligence. So now we'll actually arrive at the end of the lecture at deep learning. And so just to recap from last week. So last week we kind of reformulated our statistical learning problem into kind of a more probabilistic language. So that was kind of under the term variational inference. So we wanted to find basically do statistics. So like a posterior inference, we want to know what is the answer given some kind of input, and that in a probabilistic way. So we wanted to say, okay, what is the probability, for example, that there's a cat in the picture? And so we needed to kind of learn between like a distance between different probability densities. And so we did that using a construction called the KL divergence, which is a distance measure between probability densities. But basically, we boiled everything down into learning generic functions, which we then stick into the parameter values of like a chosen wrapping probability density. And so that's kind of the variational inference setup. So we're just saying, okay, we define like a space of densities, and we just search through that space to find a good approximation to the posterior. And then we finally also figured out, okay, what is actually kind of like a good kind of learning algorithm. So before we abstractly talked about learning algorithms, now we actually figured or formulated one concretely, which is gradient descent, which has a few nice properties in the sense that it actually also in the deep learning picture where we have this deep double descent type of phenomenon, implicitly selects very good solutions. We talked about like different types of learning setups, so regression and classification. They all both fit into this variational inference picture, but just the wrapping density is different. So for classification, we have a Bernoulli because the answer space is between 0 and 1. So probabilities is a yes. What's the probability of yes? And then there's only one other option, no. And so we stick basically we learn this function. For regression, basically we have like a posterior estimation, which is a normal density, and then we learn the mean function. So next lecture, we're going to discuss a few of these constructions in a little bit more detail before we then go on to kind of more deep learning things. So that was the basic setup, and then the example that we have is like the soft version of the perceptron, which is basically, okay, instead of so we have like this function which needs to be probability success probability of between 0 and 1, and so we needed to somehow when we have a function between minus infinity and infinity, squash it down into a function between 0 and 1, and we use the sigmoid function to get some like soft version of this perceptron where we still have kind of like a linear decision boundary, but it's like a gradient, and so that's was the setup. All right, so we can finally learn. So I hope, yeah, so we saw this at the end of the last lecture, and I hope in the exercise, if you manage to do the exercises, you were also kind of able to learn or train your first artificial intelligence algorithm. It's not very intelligent, but it is artificial. And so you can actually do machine learning now, and that's already very satisfying, maybe in some degree. but it's still a bit basic. So we did upload a solution to this exercise a bit early because it's important for you to understand how this works, because it's only going to get more complicated kind of in the future. It's going to get simple in one specific way, but generally conceptually it might kind of become complicated. So make sure you understand the solution to this last week's exercise. All right, so but yeah, as I said, it's okay, it's artificial intelligence is not super intelligent, it's pretty dumb, but you know, but at least we know how to train it. We knew how to calculate the gradients of the parameters and so on. We can do it. But from our statistical learning you know, discussion, we had this discussion about, you know, iterating through like different complexity classes of functions. And so the perceptron, the thing that we're learning here is like in the very low complexity class. And so we want to somehow be able to kind of move further to the right. And the question is, okay, I just gave you the perceptron, you know, what is like a good class of complex functions, and how do we explore that class, and how do we learn within that new, more complex hypothesis set? So that's the kind of topic of today. And so the problem is that, okay, we have this nice formula for the linear decision boundary. It's probably something that you could have come up yourself. So linear functions, maybe the first thing you try. And so, you know, it's maybe already useful for like a few problems. And in fact, you know, a lot of science and economics and so on, they all use logistic regression, which is exactly this perceptron, right? So it's not that it's completely useless. And so the question is, okay, how do we formulate something equivalent for the more complex classes? So maybe where you have like multiple kind of linear divisions that kind of connect to each other, or you have something where you have a little bit more curved lines. And so how do you formulate these types of function classes? So it's not only you want to have like one curved line, but you want to have a family of curved line, you know, where both of these things, you know, correspond to some parameter settings, right? And it's not super clear how to do this. Okay, so ideally what we want to have is we want to have basically like a smooth way and a structured way to increase the complexity of our function class or our hypothesis set, so that we can be sure that we can, at least as long as we choose to make it more complex, we can somehow find a hypothesis set where we have like at least some good understanding that it can come close to the true target concept that we're trying to learn. So if the true function is some curved function, we want to use a hypothesis set in which curved functions can be represented. We might not want to use a super large function where there are curved functions, but then it's, you know, drowned in like a lot of other solutions. We want to be really careful in how we choose this hypothesis set, but in a way we want to somehow be able to smoothly move from left to right in that space. And so how can we do it? So you can kind of take a wild guess. So, you know, why are we only multiplying and adding numbers? We can, you know, we had a lot of math classes. We can do like more complicated things. Maybe we do like some crazy square roots and exponentials and so on. And that certainly complexifies the type of decision boundaries that you see, right? And so you go from straight lines to, you know, crazy curved lines. So great. So somehow we achieved our goal, but you know, first of all, we're running out of kind of mathematical symbols to stick around these weights and biases and you know, our input features pretty quickly, right? And then still we only have these three parameters. So you know, we made the function look more complicated, but there's still only W1, W2, and P, right? So it's a three parameter thing. If I stick the, you know, put the different values, the curved lines might go somewhere else, but it's not really kind of adding flexibility. You know, we just kind of artificially made things more complicated. It's not really what we want to do. And so the question is, how do we get complexity? And so as physicists, we kind of have a very strong intuition how we get complexity, and basically it's through composition, right? So we know from particle physics that we can basically construct everything that we see around us, you know, which was only 5% of the known energy density in the universe, but nonetheless, everything, every chair, everything, we can construct through the thing that is on the left, which is the standard model of particle physics, where we have quarks and leptons. So we have up and down quarks, from which we can construct protons, and we can construct atomic nuclei, atoms, molecules, and so on. And basically, we can get our entire periodic table, which already was like a huge success to reduce everything down to this, and then we construct the world, right? And so we know that by just kind of like a very judicious use of composition, where we can put known simple things together into more complicated shapes, and then repeat this process, we can generate something very, very complex from just a few input ingredients. And so we'll basically use this intuition to generate complexity also in machine learning. And so actually, we saw already from the perceptron, we already used this type of concept already in the perceptron to generate complexity. So it's not like the perceptron is not like a trivial algorithm. It already has quite a bit of things. So you can have like decision boundary that go this way or that way or this way, right? And so somehow it's already non-trivial. And so and the reason that it's non-trivial is because we used composition. And so we can kind of look at the individual things. So if we just so we could have just used like the x coordinate one feature as a decision boundary, right? So it's not a wrong decision boundary. If let's say your class, if you have like basketball players again, it's like on the x-axis the height. Of course, like your classification accuracy will be quite good if you say, okay, if you're tall, you'll be a quite good basketball player. It's not always true, but on average might already work, and that's what we want to do in empirical risk minimization. So we could just use this first coordinate, but then what is happening in the perceptron? So it's not that we just use the coordinate, but we also scale it, right? And so we kind of change the decision boundary by not only going 0 steps, but we do 1 step, we do like a multiplication. That's already a form of composition. We compose the weight together with the feature, right? And then we also did it on the other feature. So we could have also just used kind of the raw input of the feature, but now what we're doing is we're composing this with the weight, and then we're combining the weight with the feature, and it's already also scaling it. And so now what is happening when we add these two features, and this is precisely the relationship between the two weights, is precisely what specifies the slope of that decision boundary. And so this is what we get if we get the sum. And now we have, so we already used up our W1 and W2, but by just linear composition, we already kind of generated at least like a minimal amount of complexity. And then we have our bias, which basically just shifts our decision boundary back and forth. So just that we kind of control where it starts being confident about the prediction. Okay, then what happens when we do the sigmoid is just that we flatten it into 0 and 1, because just this expression will be between -infinity and infinity. And so we already used quite a bit of composition actually in this simple formula. And it's the beauty about mathematical notation that we're very efficient in writing down very deeply nested kind of expressions without doing a lot of like parentheses and so on. But if you try to actually kind of write down what is the computational graph and like the individual expressions that we have, it kind of looks like this. So we start with our features at the top, right? And then we have our weights, they come out also from the top, and then we have our kind of multiplications. And so you can always kind of write any mathematical expression, you can write like a graph like this, right? And so it's basically also the way that you can describe computer programs. It's like a syntax tree or a computational graph that is often used to describe computer programs. And so basically we started with our multiplication, we have our multiplied values, then we add the multiplied values together, and then we add some more, which is where like an additional parameter comes in. And then at the very end, we have our sigmoid function, which squashes the function, which I didn't, I mean, you can make this as complicated as you want. This computation graph, actually this last node is 1 over kind of the sum of 1 plus e minus x and so on. And so actually it's even more composed than like this slide will tell you. And so we can kind of, this is the super resolved view on the left, and then there's kind of like a slightly more compact version on the right, where basically the colors on the edges mean that, so the strength of this edge is how much this feature kind of is weighted in the sum of the thing, and this will control the relationship between these two edge weights will control, what the exact slope of this perceptron is. And so you can see already in this very deep wall of text that complexity arises through repeated composition of very simple operations like addition and multiplications and so on. And so basically what is generating complexity is depth, right? And that's why it's called deep learning. And so we'll get to this, and whether or not we need depth and how much depth we need is still an open question, but at least you can kind of get this intuition that somehow this composition plays an important role. Okay, so now we can kind of try to complexify our perceptron. So which pieces are actually kind of non-negotiable in the perceptron? Really, the only thing for the variational inference to work is that this parameter value for the Bernoulli is basically a function between 0 and 1. And so we absolutely need the squashing function at the very end. There's no way around it, so we need to keep it. But we can kind of change what is happening upstream. So it was our choice that we would do this linear combination with the shift. And this is what we stick into the squashing function, which then produces the prediction. And so in principle, any type of function between x1 and x2, which generates kind of like the pre-sigmoid value a of x, is fair game. And so now the question is, okay, how can we generate a sufficiently complex class of functions that we can stick into our squashing function, then that will give us our prediction. Okay, so as we kind of so this was like the example that we saw. Okay, we couldn't solve, and so one of the reasons why it's difficult for a perceptron is that there seems to be two directions that play a role. So the blue dots are further to the left and to the right, and so there you would reason that somehow like the decision function that is kind of separating between left and right plays an important role. That's like an important signal to consider. Okay. Let me see. I don't have a. Does anybody have like a table for Max? Yeah. That was. Thank you. Okay, perfect. You saved the lecture, but now you need to stay until the end. Okay, so like this left-right difference seems to be important, but also the top-bottom difference also seems to be important because the blue point a little bit further upwards than the yellow points. And so maybe kind of like a thought you might have is, okay, maybe some kind of combination between the two might do the trick, right? And so one thing we could do is, okay, like the simplest combination that we can think of is a linear combination, which is also the reason why we use a linear combination for the perceptron. And so what is happening when we have linear combinations? So let's say we do this. So we compute these two kind of derived features. So they're not actually the things that we're measuring, which is x1, x2, but from the things that we're measuring, we can choose to somehow represent the data in a certain way. And so we can formulate basically two perceptrons or like the linear decision part of the perceptron. And so H1 and H2. And so H1 then it's like a certain set of weights and biases, and then H2 is somehow like a second set of weights and biases. And so it's not necessary that they're kind of aligned like this, but this was just our intuition that these two directions are important. Okay, so then what we might say is, okay, we can just do like a linear combination of these two derived quantities, and then we just because we realize it's useful from the perceptron, maybe we also do the same trick and we shift it a little bit. Okay, so what is happening? How does this decision boundary look like when once you do it? Basically, okay, so this is just like a small sketch of how we complexified it. So instead of just having one of these things, we have two internal nodes, and then we do like an additional linear combination. So what type of function do we get from this? Okay, we still get only like a linear function. So we try to make it more complicated, but somehow it's still like a linear function. So we didn't really win anything. We tried to use more complex math, but it didn't help a lot. And it's still like a linear function. And so somehow like this type of trivial combination is not doing the trick. And so we need to find like a better way. Okay, so the upshot is, okay, we came into this situation because linear combinations of linear combinations are nothing else than linear combinations. And so it's just, so you can do a little bit of math, and basically you can summarize everything in just like different weights and biases. And this is exactly kind of what happened. So we had our input perceptrons, and then they just overlaid each other to kind of generate different weights and biases. And then you have just like a different weight and bias, and then it's just another linear boundary. Okay, so we need to have a little bit more and to kind of really extract complex behavior. So we already, in some ways, the answer is again in the perceptron. So to do something non-trivial, which is maybe like the only piece that looks maybe a little bit complicated in the perceptron is not the multiplication and the shift. The complicated thing somehow is the sigmoid, right? And so it's maybe a function that you didn't know about, or like certainly looks a little bit more complicated and mathy. And so we generated kind of non-trivial complexity through a nonlinear function. So that was needed mostly for us to kind of squash this from minus infinity to infinity to 0 and 1. But at the same time, it's also somehow when we started talking about artificial brains and so on, like in the first lecture, it was also, we explained that this is like artificial neurons, does it fire, yes or no? And so it's like a signal between 0 and 1, does it fire? And now we have maybe like firing probability, but somehow it was also used as a response function. And so we can kind of use this intuition to see, okay, maybe adding nonlinear stuff, or we need to not add nonlinear stuff, otherwise we'll just forever be kind of in the land of the perceptron. And so let's see what happens once we have linear things. So we'll try something more complicated now. So we have our individual kind of input features, but now we'll squash them through this linear function. So based on what exactly the value of this input feature is, we'll now basically have a response between 0 and 1, and then we'll do like a weighted average between these responses, right? And then we'll stick that again through a sigmoid, right? And so it's basically the same function in terms of composition as we had kind of here, right? Except that kind of underneath every kind of sum symbol, we also add like a sigmoid to squash it. Okay, so then what does that look like? So hopefully we're doing better, and indeed we are doing better. So we get very nice kind of curvilinear functions, and they look a little more complicated. If you look at it closely, you might be able to imagine that, like with the right combination of what are these input features, you might be able to generate something that cleanly separates that pattern, right? Okay, so nonlinearity is really, really important. And now you might ask yourself, okay, which nonlinearity is useful and which is not useful. And so we'll get to this in a bit, but kind of the take-home message one for this lecture is that nonlinearities are super important, and it's really the thing that allows you to go, do composition and do deep learning in a way that is not just kind of collapses to like a perceptron again. Okay, so and it's not only so. We also had like these curved functions when we had these crazy formulas, right, with the square roots and so on. But this thing is different because this is we're adding parameters, and we have a lot of control what this curvilinear function is. And so there's an entire family of curvilinear functions, but has more true flexibility because we have more parameters. So why do we have more parameters? So we have these input parameters, but then also it's up to us how we combine them. And so this adds additional weights and additional biases in order to control exactly what the orientation of this decision boundary is going to be. Just to drive this point home, so we see even if we have the same input features and we kind of extract the same internal representation using our first two nodes in the graph with the sums, just by changing the nodes kind of in the second level of parameters, we can completely swap which direction this function is looking at. And so here we have the function that has high values at the lower right, and here's high values on the upper right. And this just didn't necessarily just depend on the data, but we have like added parameters, and this adds true flexibility. Okay, so now the question is, okay, what type of nonlinearity are we using? And so as we discussed, last node had to be a sigmoid because we want to use this for variational inference, and so there we need to have our output to be between 0 and 1. But for the intermediate nonlinearities, we have a little bit more freedom, and so we can kind of change our formula to be, so it doesn't need to be a sigmoid. It's often still written as a sigmoid, but let's say it's just any function. This is often called an activation function because it activates the response based on what is coming above, what is coming into this computation. And actually it turns out kind of almost any type of nonlinearity is fine. The nonlinearity's role is only to break this collapse into the perceptron. And so whatever nonlinear function you can think of, usually it's a fine activation function. But of course, there are like a few activation functions that are popular, and like the sigmoid one is actually was popular for a long time because it has this nice connection to like a biological neuron and this binary output that you might think about. Okay, so what is the dumbest nonlinearity you can find? So if we really want to make like a minimal change, we basically have a linear function, and then we just split it into two linear functions, and out comes a nonlinear function. But it's linear basically everywhere, just that it has like this little kink in the middle. And so this is called the ReLU. It's the rectifying linear unit, and it has a very simple formula. And so it's basically x if the input value is between above 0, and it's 0 on the left of it. And so this is similar maybe to this step function that we had in the original perceptron, but instead of squashing it to 1 and saying, okay, this is just firing, it also has it outputs like a scale in relation to what is coming into the unit. And so this is kind of by far, or a very, very, very popular nonlinearity to use inside of these computational graphs. And one of the reasons why it's very popular is because so one of the things that you had to do in the exercise to train the perceptron is to derive the derivative of the sigmoid function. And I mean, it turned out to be easy, but it's also not trivial. And so somebody needs to compute this. And so what is the derivative of the ReLU? Is basically 0 or 1. So the derivative is a step function. So basically when you're doing gradient computation, the gradient has like this, is it active or is it not active? So during the training, this unit is either on or not on. And this is the direct result of this ReLU structure. Okay, then there are like different ways of doing like nonlinearities. You can have what's called a leaky ReLU, where you have like this slope is not 0, but it's actually kind of sloped a bit. But these details, I mean, they're kind of advanced topic. And so if you use a ReLU for your work, usually it's fine. But you can play with different activation functions if you like to. Okay, so what do you do? So we do the same thing. We have our two kind of input features as we had, right? And now what do we get by just basically doing almost everything linear, but we only have like individual points that are negative? We still get a nonlinear kind of curvy-like thing. Yeah. Yes.
Training the game,
Yeah.
don't we lose like, isn't it bad for the training process? If like there's no accidents,
So yeah. So the question is, okay, is it a problem? So you're saying, is it a problem that if the gradient is not dependent on x?
No, it's a problem that the gradient is zero for a large portion of it.
No, so actually that's a feature because it basically allows the network to turn off certain nodes during the learning. It learns which things to turn off, and it's the same thing if you use the sigmoid. Basically, I mean, you still have the same effect that it kind of goes like if the input feature, like whatever is the computation happens here, it's also turned off, right? And so there the kind of gradient is there. The only reason is that there's really no need for all this complicated structure with this increasing smooth weight, and it doesn't matter. Another thing you might wonder about is one of the reasons why we couldn't train the perceptron is that it was non-differentiable, right? And so this is also, I mean, not like a smooth function, and so you might think, okay, what's going on with gradient calculation? But what's interesting is, okay, so the step function, what was the gradient there? The gradient is basically zero everywhere, right? And so here the gradient is not zero everywhere, it has non-zero value. And so that is, and the only thing where the gradient is not defined is kind of at the origin, right? Because there's like a non-continuity there. But basically almost everywhere there's a well-defined gradient, and it turns out that that's fine. So it's like a measure zero set of points that have an undefined gradient, but it's also very unlikely that the input feature, the x, hits exactly zero. So you're either on the left or on the right, and there you have well-defined gradients, and it turns out that's fine. Okay, so now we have our value nonlinearity. We do the same thing, and then we get a kind of nice curved thing. And so, I mean, it's not curved, it's this linear thing, and you might recognize in the examples that I had, okay, what are our function classes? We wanted to have piecewise linear things and then also curved things, and this is exactly what type of kind of curves you get, whether or not they're kind of zigzag or smooth, depends a bit on the nonlinearity that you use inside of this computational graph. Okay, so then what's kind of interesting, you might notice, is that with the ReLU, basically the input domain space is split into different regions, and that are kind of mini perceptrons internally, right? And so in this region, there's only like a linear decision boundary. Here, there's a linear decision boundary. There's a linear decision boundary. Here's also linear. It's just like all zero, right? And so that's kind of interesting. It's basically slicing the space into different regions where internally within this region you do like a linear decision, and so you're somehow using the nonlinearity to break down the problem into maybe easy problems that are only local, where like a linear approximation is fine, and that's not very much unlike maybe Taylor approximation, where basically within like a small region it's fine if you have only linear information, right? So that's kind of interesting. We'll get to this later on in a bit. Okay, so then maybe what's interesting is, okay, what do we get if we change these things a little bit? You know, if we change the weights in the first layer, or like in these red arrows, basically the input features will change, and then our decision boundary also changes, kind of in somewhat expected ways. So both of these things kind of have the high values towards 1 to the right-hand side, and so kind of you might kind of have an intuition why this particular decision boundary appears. And so it's very useful to at least have a bit of a mental model on what is going on in these types of function classes, because later on you'll use hundreds and thousands and millions of these units, but to kind of imagine, okay, how would you do like a circle for this? Let's say your true pattern is a circle. You might have like linear decision boundaries that try to do like something like an octagon or a decagon and so on, and you can approximate a circle. And so we'll see how we can get more and more complicated things as we go, but you kind of get an intuition why this decision boundary happens. Okay, so then we can also kind of recognize again our linear subspaces. So that didn't change. The only thing that changed is the way how the space is split into linear regions. And so the weights kind of control where the regions are, but then internally inside of this region is just a perceptron. But the thing is that the boundaries of these regions, they might be very kind of non-intuitive. But it's the kind of same number of subregions, right? And so generally that just depends on how many of these kind of input signals you get. Okay, so then we can, I always talk about like a computational graph, but you know, as we said, okay, there is already kind of some connection to the perceptron that we had in the first lecture. And you can kind of look at it as in terms of like a signal pathway point of view. So there are some signals coming in from the top. And then, so what does every kind of combination of this summing and the sigmoid and the nonlinearity do for you? Basically, each of these things is taking in a few signals. Then it analyzes them by weighting them and adding them. It takes some kind of average. What exactly the average is depends on the unit. And then it decides, okay, do I pass on the signal and how do I pass on the signal and so on. And so somehow it's kind of flow of information through this computational graph, right? And this is very similar to what you might imagine like a brain is doing, like every neuron gets like a few inputs, it somehow reacts to these inputs in some non-trivial way, and then fires or doesn't fire. Okay, so what's the individual unit of this thing? It's basically what we used to call in the first lecture the artificial neuron. This is kind of the basic thing because it's not only like a single unit, which is the summing or the sigmoid, because we both of these things need to work together in order to kind of generate something interesting. So just having these linear combinations doesn't work. So we need this nonlinearity, and we need to pair a nonlinearity with every kind of analysis of the input features. And so that's kind of our core unit in this type of computational graph. And so we can combine this into a single unit. And so this is how you arrive at a neural network, right? So our unit is neurons or artificial neurons. And so now basically what we constructed here by just adding, I mean, we came in with a very strong intuition, composition is important. And so we tried like the simplest thing and then that didn't work. And we tried the next to simplest thing and that worked. And so already we basically came up with what's a neural network. And so this is really the core of this lecture and all kind of neural network based architectures, as we said in the beginning of the lecture. So there's different approaches to AI, where you might have some rule-based AI and so on. And so where you maybe hard code how to play chess and which moves are. And so this is what's called the connectionist picture, because it's so closely related to kind of the biology, because you have like a signal thing and you don't really, I mean, the simple, like the operation that is happening here is not like, is this queen move in chess allowed or not? So they're like the type of decision that is happening in each neuron is extremely like almost trivial, because it's a perceptron. It's like a linear decision. Then you just think, okay, do you pass on the signal, yes or no? And so the hope is that by having enough of these, you can generate sufficiently complex patterns through just kind of weighting these connections. And so how much does one thing talk to the next? And so this is called the connectionist picture. For a very, very long time, this didn't seem promising. There were only a few people in the world that still kind of believe that this is working. And now, since we had the deep learning revolution, this actually started working. And but it wasn't kind of well accepted that this is a viable path to do it. Okay, but I mean, the general idea is, of course, very, very old. Okay, so then, well, what have we achieved? And so we achieved basically two things at once. We have our more complex decision boundaries. And so because we added the non-linearities, but we also have this reusable building blocks, because we kind of have a reusable unit. So there's like each of these red boxes is the same type of structure. So it's clear that, okay, if you have 5 of them, Okay, you could of course have 50 or 100 or 10 million and so on. And so it's not like we exhausted, like in the mathematical symbol thing, we somehow exhausted the space of mathematical symbols, but we have just like a reusable thing. We can just arbitrarily stick as many as we want into this type of thing, and then we can make our network, our signaling pathway as complicated as possible by just adding more of these units. Okay, so then we're basically we're gonna analyze what the setup here is. So basically, once you look into this type of network, there are like three classes of nodes that are special. So there's a class of nodes that has 0 inputs, and those are the inputs themselves. So like the inputs are not generated. I mean, they're generated by some mechanism, which is kind of our stochastic density of the thing that produces the data. But we don't know what it is, and the only thing that we as analyzers of the data get is just the input. So there's no dependency there. And then kind of on the flip side, there's the output node, which only has inputs and then a final output, and that's the answer that we're going to get. And then there are these internal ones, which are the hidden nodes. And the hidden nodes are basically, what do we use them for? Basically, we use them in order to build up useful data representations. And so we kind of recognize, okay, the input data, I mean, it is what it is, we measured it, but it might not be kind of in the right configuration to make a decision. And so we want to somehow find representations of the data that help us make a decision, because every single node of these things can only do very trivial decisions. It can only do linear separation. And so we need to, in order for the last node to have like an easy job and do like a linear separation, all the previous nodes need to somehow collaborate in order to represent the data in a way that allows for a linear representation. And so in some ways, these hidden nodes or these internal nodes, they're kind of like the inner working of this machine. So if you think of it kind of as a black box where you have some input and some output, something is happening internally to represent the data in a useful way, so that the last thing before the signal comes out of the box can do a simple yes or no decision based on a linear separation. Okay, so here's an example. So how complicated can we get? So we had this example where 2 of these inputs, and now we have 3 of these inputs, and we can see we can really construct basically arbitrary shapes by just kind of choosing these input features at a right way. And so we have these 3 features, and now when we combine these 3 features, we get like a nice curve, right? And it becomes very believable that we can kind of separate this type of data set, right? Because the only thing, it is separable, but the only thing that needs to happen is we need to have like kind of curved thing. We don't get true smooth kind of circles, but it's clear by adding enough neurons, and you can make these things as smooth as you want, basically. And so we'll give a name to this type of property in a bit. We can still count the number of linear regions. So again, it's the same thing. We just use the ReLU nonlinearity to combine these features. And so basically what ReLU does is splits the input space into linear subregions. Inside of each linear subregion, it's the same idea. It's a very simple decision function that happens, and the weights of this network only control how this space is going to be split. Okay, so now the question is, okay, we've seen, okay, this is what we can get with 3 internal neurons. How can we generalize? And basically, the question is, okay, as we add more and more of these input neurons, like our intuition is that we're somehow, enlarging the hypothesis space, and the functions that we can represent become more complex. And really what was our starting point in the lecture is that we want to kind of move smoothly on this complexity axis. And so the question is, okay, how expressive, how complex are the functions as we add more and more neurons, right? And so that hypothesis space might be small or might be large. If it's just like a single neuron, then it's like the same as the perceptron. If you have 2, you can have like 1 kink. If you have 3, you can have 2 kinks and so on. And then you can build up curves and whatever. And so the question is, okay, how does this scale with the number of neurons? or do we maybe need to do something else? And so, I mean, there are millions ways you could add neurons into a network like this. And so this is like a very nice and regular arrangement, but doesn't need to be that way. And so let's see what is going on. Okay, so we can do it like an exercise in one dimension. So let's start with just one neuron. And so we have, our linear decision boundary. Somehow it happens that we chose the weights and the bias that the nonlinearity, the kink is at 0. Right, and so this is what the output is going to be if we ignore all the other neurons and we just look at this, right? And so, but then what we can do is we can look at a different neuron, and for the different neuron, we have more parameters. So every neuron comes with its own parameters. And so now we're kind of in this one dimension, so we only have one input and one output. And so let's see, we have our second neuron. And so for this one, we can choose our weights and biases different, and we'll basically shift the direction where this nonlinear, where this kink is. And this is basically like a relationship between W and B. So you can say, okay, value is 0 or the kink is at 0. So WX plus B must be 0. And so it's clear that you can compute where the kink is. And conversely, if you know where you want to put the kink, you can know how to put the weights and the biases. Okay, so we chose a configuration where one kink is at 0 and then one kink is a little bit to the left. Okay, what happens if we when we subtract these two functions? What type of shape is being generated? What? Not so I mean the difference is constant on the right. Yeah, so just one minus the other. Yeah, so it's kind of like a step function. So the distance, so once both are kind of beyond the kink, the distance is constant. So here it's constant. Here somehow the difference is 0, and so now it's slowly increasing, right? Okay, so it's looks something like this. So this is the linear combination of value units, so the type of thing that we're allowed to do, and so we can generate this nice step function. Okay, great. So now let's see what happens. We can do the same thing in the other direction, and so we this is just okay. How can we get like a negative slope, like the flip version? We just use like a negative weight, right? Because then this will be kind of like a negative slope, and then once this becomes too large, then it gets cut off by the value, right? Okay, so we have our negative weight, and we can do the same thing depending on how we choose our weight. Now it's just negative, and we can basically shift our kink position to whatever it is. Okay, so now we can, so it's also just looking at a single neuron. And so now we can do the combination, and it's again the same type of idea. You can kind of get a step function, but now the positive axis is in a different direction. And so now we're getting to where you wanted to go. Is okay, can we combine these two things into something interesting? And so we can add these two things, and now we get somehow like a little bump function together. And so by adding more neurons, we can kind of get like something fairly complicated looking. It's maybe not so elegant that it's shifted to the top. So we'll just use the one more freedom. So this is a linear combination, but we had this one more shift parameter also for the second level of the kind of value of the network, right? We always had linear combination plus shift. And so we can shift it by -1, and we can just drop it down to 0. And so now we have like a nice bump function. What's nice is that we can basically position it and scale it wherever we want. By the right choice of weights and biases, we can put the bump function anywhere on the x-axis, because this just was a function of where we put these kinks, right? And then we can scale it, and then we can of course flip it around to be negative as well, because that's just like if you choose the VK in the very beginning, you multiply them by -1, it's still a linear combination, and you can just get the negative of this response without any problem, right? And so you get like bumps, and so now what can we do with bumps? And you might have a hunch where this is going. Okay, so let's say we want to approximate a generic function f of x, has some crazy shape. I don't know. I might not actually have a formula for this because it's just like the shape that is given by the data. And now we want to approximate this function. And so can we do it with a neural network that only has like this string of internal hidden nodes, and it's just like one layer. And so the trick is basically we do something like this that you might know already from your calculus course. So basically we know also from integration and so on that you can basically approximate any function by just stacking little blocks, right? And so we just have well-placed bumps, and then sometimes we want to stack bumps at the same position. We just sum everything up. If you have, you need to cover something else, you just have a nice way to stack these. Okay, this is maybe like a crude approximation, but now we can, of course, use the flexibility of our thing that we can scale the bumps to whatever width we want. So the question on, how wide is this bump is just a question on, what was the distance between these two functions where we put the king. And so if we want to make it small, then it's not a problem. But then we probably need many more bumps to kind of efficiently approximate this function, which just means that so for this single bump function, we needed 4 neurons, and so now for 2 bumps you need more, also 4 neurons, and for 10 bumps you need 40 neurons, and so on. And so you can see, okay, it's a idiotic way to approximate a function, but I mean with a lot of neurons you can somehow do it, and so you can do it to an arbitrary precision. Right, and so you can imagine you can make these smaller and smaller, and then you get a much better approximation of the true function f of x. Okay, and so this is a very important result in machine learning. It's called the universal function approximation theorem. Basically, somehow amazingly, just with this fairly pedestrian architecture where we have like a linear functions, like a trivial, almost non-linearity, and we just do it twice, then we can basically approximate any function in the world. So you give me some crazy function, and I just add enough neurons, and I will be able to approximate this function to whatever precision I want. If I figure out, okay, it's not precise enough, I just add more neurons, and then I put the weights and biases correctly, and then I can approximate it wherever. And so as we add more neurons, now we have a very structured way to increase the complexity of our hypothesis set by just adding more neurons. So we have maybe 2 neurons. So 1 neuron is just like a perceptron. Then let's say you have 2 neurons, 4 neurons, 16, 32, 64, whatever. And by just kind of increasing neurons, you make the hypothesis space larger and larger and larger. And so let's say we want to approximate some true function, which is a true pattern that we're trying to find. By just making it large enough, we'll get closer and closer and closer to this. We know there's a danger of increasing the hypothesis set because of overtraining and overfitting and so on. But at the same time, we knew it's a trade-off. And so we want to have a way to both increase and decrease kind of in a structured way how to control this complexity of the hypothesis set. Okay. So now, I mean, we're getting a little bit closer to what you might call like artificial intelligence, or something that does something useful for you, because okay, like a linear decision boundary, you need to have like a lot of imagination that it's something intelligent. Well, it's not trivial. It's useful for a lot of things, but I mean, at the same time, okay, whatever. But now, I mean, once we know that we can basically approximate any function by like this simple structure, it becomes a little bit more believable that we can do it. What's interesting is, of course, it's not like the only universal function approximator ever. Right, so there are actually many things to construct a universal function approximation. One simple way to see it is that, of course, there are many ways to create bump functions like this, right? Some kind of combination of Gaussians, for example, might do the trick. This is what's called, or what's used in kernel density estimation, where you kind of describe an arbitrary probability density with a lot of tiny little Gaussians. Like a Taylor expansion or is basically, like a universal function approximation. If you add more Taylor terms, you can get as close as you want to the true function. Fourier transforms are a universal function approximation. So what do you need for a Fourier transform? You only need sine and cosine, and then by like a nice combination of sine and cosine, you can get any function that you want. What's interesting, how do you get sine and cosine? You can actually use a neural network to approximate sine and cosine. So now you can basically do any function kind of using Fourier features, and that's actually used in a lot of computer vision things. And so so neural networks are not the only universal function approximator, but they're one. And so then the question is, okay, which one is the most efficient, and which one can you train easily, and so on. And for example, you've seen that like a polynomial. So this is what we had in exercise 2, where you had like this overfitting thing where like different degrees of polynomials. They were not like an easy thing to use, and became very janky very quickly. But in principle, with like the right combination of polynomial terms, it's a Taylor expansion. And so of course you can approximate any functions. Might not be the easiest thing to learn. And okay, so what differentiates neural networks is that they're also quite learnable. Okay, so now we're kind of at this point. We have somehow like some machine that has some inner workings, which is just kind of producing patterns, which is choosing the weights and then making a decision. And then you have 100 different parallel things that each choose a pattern, make a decision, and then you combine these decisions into like an overall vote. And so then this is kind of what's happening inside of this machine learning system. And so now we can kind of imagine that we can do something more complicated. So let's see what we can do. For example, you can classify plant types based on kind of 4 characteristic features of this plant. And so this is a famous data set called the iris data set. So there are various types of irises, and they differentiate themselves from the shape of the leaves. And so you can kind of measure the width and the length of these 2 types of leaves, and then you have 4 features. And so now it's not like a 2-dimensional space like what we've done in the last couple of lectures. It's already something I cannot visualize, but you can kind of try to find, okay, can you predict which of these 3 types of irises is in a given iris. So what you need to do, you need to, okay, I give you an iris, you need to take out your ruler, you measure like what is the length and the width of the leaves, you stick it into your machine learning algorithm, and then you get a decision. And that's already maybe quite useful in order to classify things that you don't have like a simple formula to classify it, because this is something that can be learned. Okay, so that's already great. And so we can do this kind of now it's already quite more complicated than what we had. So now it's not in 2 dimensions, but it's in 4 dimensions. You can imagine with just like 1 or 2 internal nodes might not be enough. In 4 dimensions, you want to have like some kind of complicated decision boundary, but you can imagine that this works. And so now you can go even further. And so now you can do actually something that starts to look a little bit like magic. So you can do like character handwriting recognition, right? So you can do something, okay, can you figure out somebody is writing something with their pen, and you put a camera on it, you get pixel values for, the intensity, is there ink or is there no ink? And it's very kind of low level information. And so instead of going to 4 dimensions, how many dimensions do you have here? So let's say this is the famous MNIST data set. So you have 28 times 28 dimensions, and now you have 768 inputs. And so like you and I mean, with 4 dimensions, maybe, but you and I will not be able to imagine like what a 768 dimensional space is, and we'll not be able to make decisions in that type of high dimensional space. But it turns out like a simple idiotic like single layer neural network can do it very well, and you can already train something to a very, very high degree of precision. This is just something I've done when I was preparing the lecture, that you can kind of get quite good loss, and so you'll see it's really kind of reducing nicely, and it's trainable. How we train these things is not something we have discussed so far, but you can believe me that you can train these things. And I mean, we know how using gradient descent, but of course we haven't discussed yet how to do the gradients. Okay, so now you can imagine, okay, are we done? So we somehow derive like a universal function approximator. We know, okay, we just need to add enough neurons, and then we can describe any type of function. We kind of can imagine, like for the perceptron, we calculate the gradients by hand. Now it's a little bit more complicated. And so maybe we can still do it, and so we can learn it. And so maybe we're done, and it's just, okay, whatever. We solved artificial intelligence, and we just need to learn sufficiently complicated functions. And so, but it's not the case, and it's one of the reasons why machine learning or deep learning didn't happen for a long time. I mean, deep learning is a it's like a field that is roughly 10 years old. And so, but of course, the perceptron and these things, they're like decades old. And so something is happening. And so the question is, okay, do we need do we need something more complicated? And so the universal function approximation theorem sounds kind of great, but we need to kind of look in detail. So when we say universal function approximation, it's not, so first of all, it's not a guarantee that when you train it, you find the right function. So this is a complex relationship between the amount of data that you have and the complexity class of your hypothesis set. And as we've seen in the second lecture, just making it, so I mean, you might imagine, okay, let's just add 10 trillion neurons. So we're sure that the pattern that we're trying to find is going to be in our hypothesis set. Because of overfitting and the limited amount of data, we know that this is not a good idea. And so you need to reduce the data, or you need to match the amount of data to the complexity class that you choose for your learning problem. And so just having universal function approximation, first of all, doesn't mean that you will learn the function. At the same time, also, there's this phrase like sufficient neuron is doing a lot of work here, right? And so we don't know, like if I give you some crazy function, how many neurons do you actually need to approximate this function to like a sufficient precision? And so what you want to do is, of course, I don't want to think about complexity and the number of like little microscopic kinks in the function. So I have like some larger idea on what I consider a complex function and what I consider not a complex function. And so we want to somehow know, okay, let's say we have like a conceptual complexity, which is difficult to quantify, but we can imagine we can do it. Let's say functions that are not linear but have one kink, right, or something like this. And so the question, okay, how does the number of neurons scale with the conceptual complexity, right? And so one of the things that how we can, for example, estimate the conceptual complexity is that we counted the linear subregions, right? So the more linear subregions you have that are different from each other, then the more complex the function somehow is. And so one thing you might, for example, want to count is, okay, how many linear subregions do you get for a specific number of neurons, or how many neurons do you need for a specific number of linear subregions? And so it turns out, the fear of every computer scientist, it scales exponentially. And so you can show, at least for a very, so it's by no means like a kind of like a closed research area, but you can show that for specific notions of complexity and specific setups, you can show that the number of neurons that you need in the single hidden layer of this neural network scales exponentially with the complexity, right? So let's say you want to have a function with many kind of fluctuations, up and down, up and down, up and down. You need a lot of neurons to kind of express this. And so the number of linear subregions somehow is the thing that you want to have on the x-axis, but in order to express them, you need to go really high on the number of neurons. And so learning becomes infeasible very quickly, because even if you want to have, let's say, 100 kinks, you might need to have like a billion neurons. So that's not great. Okay. Why is this not great? Because we might want to do more complicated things. So procedure that I told you on how do we do like this classification of this particle of this flower in this image, right? Is that we kind of go to the flower, we measure the thing, the 4 things. We know we have a machine that takes 4 inputs, and then it will maybe do a very good job at telling us. But okay, if it's first, like it requires us to do something for the machine, and so we need to go to the thing, measure it, and so this is cognitive work that we're doing, and then we need to stick it into our machine, and then this is our prediction. And so let's say we wanted to do something more ambitious, where we actually want to say, okay, I give this image to the machine, and it will tell me whether or not what type of flower or what type of iris it is. And so how many inputs do you have? So here in this particular image, you have 640 and 520 pixels, because it's an RGB image. You have 3 channels, and so you have roughly like 1 million inputs. And so even though, so now we want to have like a complex function, because it's not going to be an easy function. So we want to have a complex function in a 1 million dimensional space. And so you might want to imagine how many neurons do you need to slice up a 1 million dimensional space into sufficiently complex linear subreaches in order to make this decision and so on. And so it's clear that this might not work, right? So, or it might at least be very, very complicated. And so we need to somehow find a better way to do it. And so our intuition, so let's go back to where we started, is like, okay, we found like, okay, we said composition is important. We started to compose a little bit and we stopped, right? Because somehow we were happy. We found the universal function approximation theorem. We did like 1 more layer, and then we, okay, whatever, we'll find, and we do it. But, you know, again, as physicists, we know that kind of, we don't get kind of the entire world just from doing like 1 level of composition, but we want to do multiple level of composition. So we go from quarks to protons, neutrons, nuclei, want to add electrons, you have atoms and molecules, DNA, humans, and so on. So actually, it's like a not that long composition, which might tell you something about scaling, right? So let's say you increase the number of the effective complexity class by a factor of 10 for every kind of additional layer. You know, once you go like 10 layers deep, you have 10, you know, like an increase in complexity in 10 to the 10. So this is an exponential increase in complexity just by using more levels of composition instead of trying to do like a composition of many, many things at once. And so somehow the complexity scales with the log of the number of layers that you have. And so that's a very, very, you know, advantageous type of scaling. And so we'll get this in a bit. And so then we can kind of match this to not only how do we generate data. So this is kind of like the generative process. How do we get stuff? And then the question is how do we understand stuff? And it's also we use compositions from simple concepts to complex concepts. And so here you might think, okay, like we don't know, of course, how our human perception works, or I mean, we might understand like a little bit, and if you're in neuroscience and so on, but you might imagine kind of what's going on, or at least you have like some, you know, post hoc explanation what you think you're doing. So maybe we're doing like some contrast detection that we see, okay, where are the bright spots and the dark spots. You know, maybe we have like some kind of edge detector to see, okay, which maybe depends on the contrast detection. So in order to detect an edge, you need to detect contrast and color levels. Then maybe you want to do not only contrast, but color. We want to separate background and foreground, curve classification. Maybe you want to say, okay, if this is, so if you have like a very kind of elongated leaf, you know, then probably there's like a very steep curve, right? And whereas if you have like a, you know, equal width and length, then it's more like a circle. And so being able to classify the curvature of a curve might be useful to do this type of task. And then you might want to say, okay, not only foreground and background, where in the foreground and are the actual leaves, and because this is something that I want to look at. And then you kind of at some point arrive at a overall classification. And then, you know, maybe, okay, you find this is Iris setosa, instead of, I don't actually know if that's the right answer, but okay. So basically, when we reason, at least we like to think that we do lots of intermediate calculations, and when we reuse the results of these calculations for some further calculations and so on and so on, and we compose like all of these things into some overall type of reasoning thing, and this is basically like a program that runs. And so if you write a computer program, you know, like probably your computer program is not just one line, but it's many lines because you're doing some compositional computation. And this is also expressible as a computational graph, which is deep. And so there's a nice equivalence between reasoning or proofs and programs, which I'll not get into, but you might want to look that up. Okay, so then this is maybe our inner workings, and so somehow like depth and more composition seems to work. And so now we can kind of see where we're going. So we want to go beyond a single layer. So nobody, of course, forced us to do a single layer. It was just like the simplest thing we could do. And you know, it's useful, like if we think about, okay, so what was complicated in exercise for the third week exercise to do the gradient? It was just that you had lots of functions that kind of are chained together. And so you can imagine the gradient computation becomes harder and harder the more deeper you go, because the chain rule just adds. And so like going wide actually for the gradients is very easy. But okay, nobody kind of told us that this is the only way to do it. So we want to maybe go deep instead of wide, because now what can happen is that these guys can be like preparatory guys that you know, kind of prepare some data representation, not for the final answer, but then for the next level of decision making. And then that prepares the answer for the final decision making, where it needs to be simple enough to do like a linear separation. And so now this gives us kind of like an opportunity to build up very complex things by just doing simple things, but in a very highly repeated fashion. Okay, so then this kind of gives you to a kind of deep learning philosophy. And so basically, in order to make shallow learning work, because we understood we cannot learn a shallow network with 1 trillion neurons, right? So it's not super easy. And so the effective complexity that is actually trainable for the shallow network is only like a very, somewhat medium scale that we can do like simple things, which are not so simple that we can do like character recognition and so on. Is already much more useful than the perceptron. But somehow like, okay, this will not kind of produce artificial general intelligence. So we need to somehow prepare as humans the input in a way that the machine understands, where the machine can only do like, so, you know, like a certain degree of complexity for us. And so basically we are the assistant of the machine, or the other way around, depending on how you look at it. But we are producing these input features, and then we stick it into the machine, and then we do a prediction. What the deep learning philosophy is that we're basically, instead of us trying to do this type of preparatory work, we just ask the deep learning system to do it itself, and just kind of figure out, okay, what is the right level of complexity that you need in order to arrive at the solution. And the hope is that internally, you know, it will find the relevant pattern at the right complexity class. So it will learn to distinguish between contrasts. It will learn to recognize edges. It will learn to find curves and so on, and textures of fur versus you know, human skin, and these types of things. And it turns out that happens. And so, but this is basically, okay, we just you know, compose in a very deep way. And as we said, this will give us an exponential increase, and then we can have like we kind of did a lot of preparation, and then finally the task is simple enough that this kind of version of the multi-layer perceptron is sufficient to do the final thing, right? And very often you have neural network architecture where you have maybe some complex architecture, and at the very end there's just like a little multi-layer perceptron at the end that does the final prediction. Okay, so this is then what it looks like. So the easiest way to build deep nets is to just stack these neuron layers. So we had like one layer, and now we just stick more neuron layers. And so what does it actually do? So let's say you have 10 input neurons and 10 output neurons. So for every output neurons, you have like a weight vector, which is dimension 10. So because you want to do like some linear combination of the 10 inputs, but then you also have 10 outputs. So what do you have? You have like a weight matrix. And so in the end, what you have is like a matrix multiplication for between the inputs of the layer before, so the hidden layer for L minus 1. And then you have the weight matrix, and then you have the bias for every of the output neurons. You have like one shift that you can control. And then afterwards, we remember, okay, if we just add like a matrix multiplication to a matrix multiplication, it's nothing else than a matrix multiplication. So linear combinations of linear things are linear. So we needed to add this nonlinearity. But this gives us a very kind of nice picture on how we can compose multiple layers into a neural network. And without any problems, we can have 10 or 15 or whatever layers. And this is essentially already deep learning. And so this kind of construction is called the multi-layer perceptron. And so here, basically, the only thing in this notation that is important to understand is that the sigma is like an element-wise operation. So like for every of these nodes, you need to apply the nonlinearity to that input. Okay, so this is really kind of the workhorse of deep learning. If you're not sure what architecture to use in your network, you just want to use like a baseline architecture, just use like fully connected. So that's also sometimes called a fully connected network because every node is connected to every node. Yeah, just use that and see how well it's done. And then if it's not sufficiently good, you can still try to improve it by some architectural tricks, which is going to be the bulk of the lecture going forward. But that already works quite well for a lot of different things. Okay, so you might look at this thing and say, okay, this is basically, so the vast majority of computations is just matrix multiplication, right? And so basically, deep learning is just matrix multiplication to a very, very large degree. And somehow in the way that you use CPUs. So the CPU is very good at very general computation. But the only thing that we're doing is matrix multiplication. So also from a hardware level, the way that we build the GPUs, they're built to, play chess and so on, because we used to kind of, implement algorithms like fast Fourier transforms and whatever. So then the CPU is built that way. But now, like if you imagine, or if you recall the second lecture, we said, okay, learning is basically a different way to write software, but the complexity of the software is not in the complexity of the program. The program is very simple. It's just matrix multiplication. The complexity is in the actual values of the weights and how many of these neurons you have. And so actually what the hardware sees is very simple, and that's why GPUs became so important in deep learning, because GPUs happen to be extremely good at matrix multiplication, and somehow the only thing that you need for deep learning is matrix multiplication. And so now people, like the same way for like Bitcoin mining, people started building their own chips that only do Bitcoin mining. All these AI companies build chips that can basically only do matrix multiplication. And then, of course, if you don't need to do all kinds of crazy like exponentials and sinusoids and whatever, of course, you can have a very, very efficient hardware to just do matrix multiplications. And it's really kind of like it's a deep change in the way that we build computer architecture. And it's the way that we can actually still get Moore's law running. So Moore's law is the thing that, like the speed of computers or the performance of computers doubles every 18 months. Kind of in the early 2000s, this stopped happening for like the speed of single core processors because of heating constraints and so on, and just like you didn't get more gigahertz for your processor, right? And so then people went into multiple processors and so on. And so now this is also stalling, and because you cannot compute this, you cannot write your software in a way that is like very efficient in parallel computation. But actually, it turns out that the number of transistors that you can put into a chip didn't stop growing exponentially. We're still in Moore's law. There's still an exponential growth in transistors, but the way that we kind of matched our software to our hardware stopped scaling. And so now we can use these transistors to just implement matrix multiplication. This will carry us a little bit longer into Moore's law. And but in order to exploit this, we need to express our logic in matrix multiplications. The way to do that is machine learning. All right. So how expressive are these deep networks? So the kind of true relationship between deep networks and shallow networks is kind of still an active area of research. What we can say empirically is it's just when we train deep networks, they can more easily find and generate complex patterns with much fewer parameters, because you get this exponential increase of compositions, which is true kind of intuitively, but I mean, to prove it kind of in a super general way is not easy, but and as I said, it's being done in like a certain constrained situation, but it's not completely clear yet. Okay, but now if we can kind of draw this line, basically you can if you have like a fixed budget for a number of parameters that you want, with deep networks, you can reach much higher conceptual complexity than with shallow networks, even though both are universal function approximators, but it's just deep networks are better at learning than shallow ones. All right. Here's an example from this is what we had in the block course. So here you have like a very simple like eggshell pattern. So you have kind of alternating regions of class 0 and class 1. And so you can imagine it's a very complex situation because you need to always change the prediction boundary very quickly as a function of the space. And so here is on the right-hand side, you can see what the training curve looks like as you're training deep neural networks. On the x-axis, you have the number of training steps. On the y-axis, you have the empirical loss. And so you can see, okay, universal function approximation, if you just add enough parameters to a shallow network, it will have no problems in learning this type of complicated function. And so here, for example, in violet, we have 28,000 neurons, right, which is a 28, a 2 matrix and so on. I mean, 28,000 times 2 matrix, so it's a complicated matrix, but it's, okay, fine, 28,000 neurons, it will learn the function. Okay, but you need 28,000 neurons. So if you do like 1,000 neurons or here, and you're increasing your hypothesis set to go to 2,000 neurons, 6,000 neurons, and so on. And the more you're adding neurons, the truer and truer the universal function approximation becomes. But then now you go to a deep network with 1,000 parameters, and then you're much faster even than a network with the 28,000 parameters. And so this really shows you the advantage that you get. So let's say you want to have like a fixed performance on how quick let's say you're fine if the performance is at 0.4. Like with the deep network, you don't even need to train for a super long time, and you will get there and you'll get to this 0.4, and even with 6,000 parameters, you'll never get there, right? And so it's not just like a trivial difference between deep and shallow networks, but it really kind of is the difference between things work and things don't work, because it's an exponential type of effect, at least empirically. Okay, so then the question is, okay, what we didn't discuss yet, so somehow last lecture we kind of finally got our learning algorithm, so we got our gradients. If you look at the solution of the exercise, you see, so for every single little kind of atomic operation, like the linear combination, the sigmoid, the loss function, and the empirical risk, you always had to kind of add like a gradient computation, because it's the chain rule that links these things together. And so now imagine you have like lots of deep computation. Since the computation is always the same, like, okay, you might actually get away, and it's just like a matter of correctly wiring everything together. But it's already, I don't know, so who managed to do this in the exercise? Okay, a few. So when I designed the exercise, I made lots of mistakes, and it was just painful to get all of this right. And okay, it's doable, but it's just, okay, whatever. And it used to be, as I said, in papers, people would have like appendices that this is the gradient calculation. Then, of course, there were typos in this appendix. And then if you try to reproduce a result, you would kind of add more typos and so on. It's just horrible. And so we didn't really discuss how we can, the more and more complex our deep network becomes, how do we compute gradients? And can we actually still learn? So finally, we went out of this theoretical realm and finally got something working and learning. And so we don't want to fall back into the space where we can't learn. And so what is the gradient of this thing? And then, you know, also what we didn't discuss. So somehow, okay, we had our signal layer was a universal function approximator. Somehow, like we managed to figure out, okay, this is not enough, but it wasn't because it wasn't like a universal function approximator. Somehow we noticed, okay, it's a universal function approximator, but it's super inefficient, and then we wanted to go deep. Nobody guarantees you that, okay, just going deep is enough, right? Okay, it might be the same thing, that maybe there's like some other thing that you can add where it becomes even more parameter efficient, right? And so ideally, if you just think of, okay, you have like a bunch of neurons that you can place, what these links are between the neurons and how many neurons you have between them, and you know how deep they effectively are and so on. They might not be arranged in layers. So it's complicated, and basically what this describes is an arbitrary program, like a computer program. And this doesn't make, so first of all, do we need this? Do we not need this? We don't know. Like if we want to exploit all those hardware gains, we better stay in a world where we can express everything as matrix multiplications. So it's not clear that you want to go to the right-hand side, but okay, maybe you do. And so this is something we'll discuss. But then, of course, once you, let's say we want to do this, okay, it's even more complicated. How do you compute a derivative of an arbitrary computer program? It's not obvious, and okay, I don't want to make more mistakes, and it's just horrible if you use complicated things, and it's not only matrix multiplication. So these are basically the things that we're going to discuss next week, and then we'll actually train deep neural networks and find all the beautiful architectures that are in the work. All right, thank you. Any questions? Yeah. It's a good question. It's exactly the thing that I suggested. It's basically through Fourier transformation. So you show that a single dimensional universal function approximation kind of goes like this with these bound functions and so on. And then you say, okay, if you can do sinusoids, and then it's only like a linear combination of inputs that you stick into the sinusoids and the weighting, which gives you Fourier transformation in n dimensions, and then you have universal function approximation in n dimensions. Any other questions on Zoom? Okay, doesn't seem to be the case. Okay, thanks everybody. Have a good weekend and see you next week.